Our next speaker is Sepehr Assadi, and he'll be speaking this time really on streaming algorithms. I think, at least the title says so. A slightly sublinear space streaming algorithm for matchings.
I think it's on. No? Everybody can hear me? All right, good, perfect. So let's start. Thank you, everyone, for coming here. Thank you for organizers. All right, so I'm going to talk about this result. This is a problem I know some people here have worked on, so let me not overpromise. This is a very slightly sublinear space algorithm. I'll find it still very interesting. If you've thought about it, you'll find it interesting. If not, I'll try to motivate it and why I think it is very interesting. Good. This is joint work with Sohail, Sanjeev, and Juan. Sanjeev is here. I don't know if Juan is here. Sohail is not. Good. The paper is available on arXiv under this name. I should say this thing that I'm only presenting half of the paper, which is on a streaming because I like a streaming more, but there is a part on dynamic graph algorithms as well. Good. Okay, so let's talk about the problem and definition and its history. We are talking about maximum matching. If I give you a graph, a matching is basically any collection of edges that do not share vertices. Okay, this is a matching here. And in maximum matching problem, I want to find a matching that has the largest number of edges. We are working in the graph streaming model, so this is truly a streaming result. Good. I have this graph G. The vertices are numbers 1 to n. I know everything about the vertices. The edges are completely unknown. They are coming in a stream to me. Okay, so I'm seeing in some arbitrary order. I don't know what is the order. I don't know what are the edges. I'll just get to see them in a stream. After they pass, I have to process them during the time they're passing. After they pass, I have to output a matching of the graph, preferably a large matching or good approximation. This is the problem. Sounds good? And this is a model introduced by Feigenbaum et al. Almost 20 years ago, roughly. Good. So this problem has two trivial solutions. Okay, what is the first one? Just store the adjacency matrix of the graph. Okay, whenever an edge comes, store 1 bit. You need n square bits. You store the entire input. When the input is finished, run an offline in-place algorithm that uses roughly order n square space. You get the maximum matching. Everything is good. So this is trivial algorithm 1. Trivial algorithm 2 is to, whenever the edges are coming, greedily pick them if you can add them to your matching. That will give you a maximal matching. It's a simple exercise. This is a half approximation. The space you'll use is order n log n space in terms of bits. And n log n is needed to store any constant factor approximation matching. So space-wise, this is very good. Okay. The first result is also optimal in the sense that if you want to find an exact maximum matching, you need omega n square space. You cannot do better than that. It's a simple reduction from index problem. And the second result also, again, was it's a simple observation. You can do this. So these two, the first paper that introduced graph streaming, said there are these two results for this problem, this trivial algorithm. The question is there any non-trivial algorithm also for this problem or not? The short answer is that so far, no, we don't know anything like that. Let me give you a bit longer answer because matching is arguably one of the most studied problems in graph streaming. So what are people doing then if there is nothing known here? There are lots of variants. One is that there's lots of work on weighted matchings. Without getting into details, the final work here is basically saying whatever thing you can do for unweighted, there is this compiler that just takes it and ports it to the same result for weighted by losing some dependence on epsilon in the space. Okay, there are some terms and conditions here. This statement is definitely true for bipartite graphs. For non-bipartite graphs, there are some other conditions. Okay, good. There are also lots of work on multi-pass streaming algorithm. Basically, started by this work of Andrew that says you can do 1 minus epsilon approximation if you have something that depends, number of passes that depends on epsilon. There are lots of work that optimize this function. For here, just note that these results are really based on some iterative optimization methods. They're really multi-pass, okay? You need 4 or 5 passes just to start getting something non-trivial from them. So they're very far from the original problem that I defined. So more related to the question, what do we know? There's this nice paper by Goer, Kapralov-Khanna that proved the first lower bound for this problem. If you want to get better than 2-term approximation, you need this much space. Just think of it, this is larger than any n polylog. Okay. Another important part of this paper is that it's introduced the use of Ruzsa-Szemeredi graphs that I will talk about later in the talk to prove a streaming lower bounds for matching. And then later on, these results have been used left and right in proving a streaming lower bounds now. And this bond that you're seeing, this is basically the density of best RS graph that we know. And this bond has still remained for like 20 years, more than that probably. So that's one part. There are some lower bounds, and this lower bounds were improved. Michael Kapralov proved 1 minus 1 over E requires this much space, and more recently, even something better than 0.6 approximation requires this much space. One note here is that these two spaces, they are white box application of RS graph. They hold because of the technique used to prove the lower bounds. This means that even if you improve RS graph upper bound, lower bounds do not necessarily improve this bounds, okay? Unlike the previous result that I said. Okay, one last part. So there is also this very nice paper by Conrad et al. They wanted to solve the half approximation problem and say that what are some relaxations I can make so that I can solve this problem. And one thing they said, in random streams, you can do it. Also, if you have two passes, you can do it. I want to say that don't see this result as a multi-pass algorithm. Think of it as a tiny relaxation of the single pass model. I just give you one more pass. The goal here was to basically get techniques for beating factor 2 in a single pass. Okay, good. And there have been lots and lots of follow-up work here. I don't know how much these people still believe that these relaxations are going towards solving the original problem, but they are now being studied on their own, and there are nice results here. You can get all the way even better than 2/3 here, and you can get all like close to 0.54 for two-pass algorithms. So, summary, what's going on? Lower bound, n square space is needed if you want the exact answer. Better than 2/3 depends on density of RS graphs, and better than 0.59 requires this much space. Lower bound, this is what we know. Upper bound, we don't know anything for the original problem. If we do some relaxations, like two passes, random order, or vertex arrival, we can solve the problem. Good. So now with that in mind, let's talk about our result. So our result is we give a deterministic 1 minus a small o of 1 approximation algorithm in a small o of n square space. Okay. The important part here is not really that it's 1 minus a small o of 1, it's that it's better than 2. Okay. And so the takeaway is that you can do something non-trivial for a streaming match. Good. So sounds exciting, everything is good. So now I have to tell you the truth. This is really, we are really banking on the definition of a small o of n square here. What it means is that a small o of n square in our result is n square divided by 2 to the theta of log star. Okay, so for any reasonable number, we are dividing by 10 or I don't know, 32 maybe. Good. Questions? Good. Okay. And log star, I assume you know the one. Iterated log, take log enough number of times so that it will become one constant. So, but why does it matter? There's two ways. First, it rules out trivial bounds for the problem. Okay. There are non-trivial things you can do. The right answer is not n square or half approximation. There are things in the middle. Now there is actually a separation. You can do better than half approximation compared to what you can do for exact matching. So complexity-wise, let's say there is a separation between the two. It's based on an entirely different set of techniques compared to what has been done for those other relaxations. It's some sort of a sparsification techniques that have been very useful in streaming. They are now applied to this problem. One important thing, whenever you talk about shaving some factors, there's this question, oh, maybe I can apply some for Russian or something like that. I shave off log n is always easy. Maybe, but if you can shave off a log n or any factor better than this, you are proving better RS graph upper bounds, okay? So there is a result, this JKK paper that says, if you can improve the space of our algorithm, you will give better RS graph upper bound. I don't know how challenging you'll consider that. It's a hard problem still, okay? If you want, you can take a look at this paper, for instance. It will have some nice consequences if you prove better RS graph upper bounds. I would say that if you prove that, that is a much nicer result than what you get from beating like a streaming matching by log n factor. Yes. Good. It means that there exists, you are proving that certain family of RS graph with some density that I can tell you a bit offline about you that cannot have more than n squared divided by 2 to the theta log star n edges. Okay, this bond correctly comes from Fox's triangle removal lemma. That's the only way we know how to bond RS graph of that certain density. If you are getting better algorithm, this will imply that you are bounding, you are giving a better way of bounding density of these RS graphs. Questions? Good. One personal note, why this thing matters to me. This is the first problem I heard when I met Sanjeev, I think like after 20 minutes of meeting him 10 years ago when I started graduate school. So it's fun that after 10 years of working directly or indirectly, there is like 2 to the theta log star on factor improvement. So that's cool. All right. So now let me tell you more about our result, how they work, and how do we get them. So it's a combination of a bunch of results, and they progressively become better to what we want. The first one is that we give a randomized algorithm that computes a matching cover. I'll define it in a second. In polynomial and linear space in n squared divided by polylog star. Okay, good. So what is a matching cover? In a simple word, it's the same thing that a cut sparsifier is for cut, matching cover is for matching. What it means is that an alpha matching cover, given any graph G, is a subgraph of G such that size of the matching between any two pairs of vertices, sorry, two sets of vertices is preserved in the cover. Okay? So if this is my graph G, I have these two sets A and B. Let's say they have this certain matching between them. In my sparsifier H, I want to have another large matching between the two. Okay? You may not share the same edges. These edges are completely different, but there is still a large matching between A and B. Okay? If you think about it, it's very easy to see that you need the approximation to be additive. A multiplicative approximation forces you to pick all the edges of the graph, always. Okay, good. So this is the definition of matching cover. And what we show is that there is an algorithm that finds one of them that uses sublinear in n square number of edges. Okay, and the algorithm is like constructive in polynomial time and linear space. You can do this. I should say that the notion of matching cover was introduced in this GKK paper. They proved their existence for bipartite graph, but it's not constructive, or it's not an efficient algorithm that creates them. So we create them efficiently, and we do them for non-bipartite graphs. And the proof of here is based on Szemeredi's regularity lemma. If I get a chance, I hope to show you this proof, actually. And this is the part that has further application to dynamic graph algorithm. Just to say what was the application, it gives a sublinear time dynamic algorithm for getting a 1 minus a small of 1 approximate matching. Okay, and a small of n is again n divided by polylog star. So that's result 1. We can get matching covers. Result 2 is that a streaming algorithm that can combine these matching covers in a clever way during the stream so that you can compute a matching cover of the input at the end as well. Okay. The previous result was not a streaming algorithm. It was an offline result that says, if you give me the graph and I have it in front of me, I can compute the matching cover. Now I'm telling you how to compute it in a streaming. It's a bit of a mouthful really to parse this. So let's go through it. So first, the result works for any integer k. Think of it, this is a parameter that you tune. So pick any integer k you want. The space you are paying is n squared divided by k plus this term. What is this term? This is, if I give you the graph in front of you, not in a streaming fashion, I've stored the graph for you. How many edges do you need to compute this type of a matching cover? Okay. Sounds good? So I want to be able to, given the graph that has n squared over k in an offline manner, the graph is in front of me now. I just have to, in an offline manner, compute a matching cover of it. How many edges my algorithm is going to pick. And the only requirement is that that algorithm should not blow up its space. If I give it n squared over k edges, it should work roughly in n squared over k space as well. So it's a way of turning an offline algorithm for matching covers and turn it into a streaming version. And these are the bounds we get. One thing now, what about this K? Well, you have to fine tune this K. Basically, the more you increase K, you reduce this factor. No, this is dropping and a square divided by K. But this part is increasing, okay? Because if you reduce K, you are asking for better and better approximation of matching cover. So you want a more accurate version. If you want more accurate version, it means that you have to store more edges. So there is a balance between these two. The reason I'm saying it in this phase that this MC is not a very easy function for us to know how it looks like exactly. So I'm just going to state it this way. Whenever you figure out what is the MC you want to plug into your function, then based on that, you pick the right K. Good? In fact, for our result, the first result at least, you can pick K to be some polylog star n. You just put these two results together, and this immediately gives you a randomized 1 minus a small of 1 approximation that shaves off some polylog star n from the space.
Positive, but not 1.
Yeah, it's like 1 over 10, 1 over 6 maybe, something like that. Yeah, good. Any other question? Maybe I should repeat the question. The question was, what is omega 1 basically here? What is the number? It's like 1 over 10, 1 over 6, something like that. Okay, good. So now let me move on from the matching cover and let me give you, matching cover is an algorithmic thing, let's say in some sense. I want to give you another algorithm, except that the role of that matching cover function is replaced by this RS graph function, okay? This is the maximum density of RS graph on n vertices and induced matching of this size. If this sentence means something to you, good. If not, I'm going to define it in a second. But before that, see, previously I had an algorithm that uses a space based on the best matching cover I could compute. Now this is an algorithm based on a structure, existential result. If the RS, this is basically how dense certain graph can be. Depending on that extremal result, the space of our algorithm is governed by that. Okay, good. So what are RS graph? Let's start. What is an induced matching? If I have a graph, an induced matching is a part of the graph, is a matching in the graph such that there are no edges between its vertices. The induced subgraph of the graph there is a matching. That's what I call an induced matching. Good. Now, RS graphs are this nice family of graph that an RT-RS graph, you can partition its edges into T induced matching, each of size R. So this is a 3x4 RS graph. This is one induced matching of size 3, another induced matching, another, and another. Okay, so it has 4 induced matching of size 3, and I partition its edges like that. We want RT-RS graph where both of these parameters are large. And if you think about them, they're very magical. And induced matching is a very, very sparse part of the graph. When you look at that part of the graph, there is a matching and nothing else. But if R and T are large, the graph globally has to be dense. So it seems like these things should not exist, except that they do. And there are lots of different construction. Perhaps originally with the work of Ruzsa-Szemeredi, they showed for some R equal n divided by 2 to the theta square root log n, you can have very, very dense RS graphs. There is a nice work by Fisher et al. And including Gronit that says you can even have your induced matching almost linear size and still pack more than polylog n of them in your graph. Okay? So that's the construction. On the lower bounds or on the upper bound side, let's say, the bounds are much weaker in some sense. We know that by Fox's triangle removal lemma, if you want near linear, sorry, not near linear, if you want like linear size induced matchings, then your graph cannot have more than n over 2 to the small of log star n induced matchings. Okay, so the graph cannot be completely dense. It will have to lose some 2 to the theta log star n edges. And we know a slightly better bound of roughly n divided by log n if you want the induced matching to be very, very large. Okay, it's like almost half of the vertices are each time getting matched by it. Then you need to have even n over log. for us, now that RS graph function that I define is the density of this graph when I have n vertices and induced matching of size beta times n. And for our purpose, the important thing is that if you want a slightly sublinear in n induced matching size, think of it n divided by 2 to the theta log star n. Still, this graph cannot be super dense. They can have at most n squared divided by 2 to the log star n edges. Okay, so this follows again from Fox's triangle removal.
Sorry, but maximum density means number of edges.
Number of edges, yes. Oh, good. So the question, what is maximum density? I mean actual number of edges. I don't know why I call it density. So how many edges are in the graph? Okay. And like among all RS graphs that have this property. And I'm saying that it cannot have more than n squared divided by 2 to the theta log star. Good. So if we come back and we put all these things together, now we have some bound like this. This is good. Okay, before that, 1 second. Based on the bound that I showed you about RS graph, if you plug in the right numbers, you can upper bound the space of this algorithm. One thing here is that this is an algorithm that we bounded the space by the density of RS graph. RS graph have been used a lot to prove lower bounds for streaming. To my knowledge, this is the first time we are using them as a way to upper bound, like as an algorithmic tool or upper bound the space of the algorithm. And the way this result works is that we use the matching cover algorithm and use a result of GKK that shows how to bound the matching covers. There is a close connection between matching covers and Ruzsa-Szemeredi graphs, and we use that connection. And that again requires some non-trivial extension to general non-bipartite graphs. Good. So good. Okay. Now, if we take a corollary of this result tree and current upper bounds we have for RS graph, this is going to give us a randomized 1 minus a small of 1 approximation in this much space. Okay. There's one further step that you can de-randomize this thing. You pay a bit more in this theta function and you de-randomize it. That part is not hard at all. Which gives us that deterministic result that I talked about. Important thing is that this is now exponential time. It's like based on enumeration. We don't know how to find that matching cover. We just find the best matching cover by going over all possible edges and figuring out, is this a good matching cover? Is this a matching cover or not? Okay, good. So how much time do I have on it? 5 minutes, good. One thing I want to say is that what happens, this result works based on density of RS graph. So what happens if the current upper bounds are tight, current lower bounds are tight actually? Okay. Any improvement you have for RS graph or will improve our algorithm. Based on the current state of the knowledge, it is possible, basically, if it so happens that the current lower bounds are the right answer to the problem, then the space of our algorithm can improve all the way to n squared divided by 2 to the theta square root log n. This is shaving more than any polylog n factors. Let me emphasize, this is if the current upper bounds, like lower bounds are tight. I have no conjecture that's the case or not, but this is the limit of our approach, basically. So I want to spend a couple of minutes telling you about high-level ideas. I will only tell you about how we get a matching cover from regularity lemma. If you're interested about the rest of them, come chat with this or see the paper online. So I want to show you how to get this result, a matching cover from regularity lemma, how we are using. A quick recap of regularity lemma with lots of oversimplification. Okay, this is very informal. It says something like this: pick any parameter epsilon. You can throw epsilon fraction of vertices out. Think of this, these are noise. I make no guarantees about them, throw them out. For the rest of them, you can partition them into this Tauber function of 1 over epsilon. That's why you get a log star factor. This is like you partition into a function of epsilon, but a crazily large function of epsilon. You partition them into these many groups, C1 to Ck, such that the following is true. Again, ignore epsilon fraction of these pairs, okay? For the remaining pairs, you can think of the pair as being roughly a random graph, okay? And roughly a random graph means they are epsilon close to being a graph, a random graph whose density is similar to the density of the edges between the two pairs. Okay? Really, for the purpose of this discussion, think of it, they are epsilon close to being random graph. Okay, good. So that's what regularity lemma does. We will use a constructive version due to Alon et al. So that we can actually get an algorithm out of that. Okay, good. So how does the matching cover algorithm work? How do we get a matching cover? You first apply the regularity lemma, you get the partition, you store all these edges. Any edge that is incident on the noise, there's no guarantee about them, just store them. Any edge that is inside the groups, store them. Any edge that are between non-regular pairs, store them. Any edge between two regular pairs whose density is not high enough to be sufficiently random, store them. Then, when you did all those things, you look at the remaining edges, you subsample them. You sample roughly n log cube n of them, and you store them. Okay? One thing, when you say these many things, it feels like, oh, wow, I'm storing lots of edges. All the edges of the graph are here. Okay, these are all exceptions. If you think about it, this is the main part. So we are sampling lots of edges of the graph. Okay, that allows to make the graph sparser. You can go through this thing. It doesn't matter. There are like these different type of numbers you get for each part. There's some numbers there. If you tune the parameters right, they will be sublinear. For right parameter epsilon to be log star, and all these things will become the type of thing we want. So the matching cover size is easy to bound. So we have it. So it's a small. But why is this a matching cover? Let me show you. I'm talking about the maximum matching MS star. I'm actually not really showing you it's a matching cover. I'm showing you that the largest matching in the graph is preserved at least. Okay. Then you apply to every pair separate. Why the largest matching is preserved? So fix that matching. Let's how it looks among the regular pairs. You don't care about all the other edges. You store them. You have those edges of the match. You have to worry about these ones. This is a simple probabilistic claim. I mean, at this high level thing that I'm saying, I can say anything. So they were randomly looking. So if you have a large matching between these pairs, you can also random samplings will preserve them. So everything is good. The problem here is that this MS star is scattered between all these pairs. Okay. So the thing is that it may use a very small number of edges between each pair. Random sampling preserve large matchings, but because I scattered my maximum matching across all these pairs, I don't have a large matching between every pair. So there's no reason I can preserve it. So the main step of the argument is that we are going to look at our matching MS star, and we are going to massage it, move it around a bit without reducing its size by much, but consolidating its support somehow between the pairs. We are saying that, look, if you had a large matching, you also have a large matching that uses a few pairs, but use them heavily. Okay? And this is some sort of a fractional matching argument here. So now that we've done this, then random sampling can preserve these edges. Okay? And you preserve these edges, and then you'll get the result. Okay, good. So I definitely have to stop. I'm going to skip all the way things about a streaming matching. Good. Oh, let me just say one thing, because I found this very interesting when we were working. When you are shaving off such a tiny factor, some annoying details happen that you never have to deal with otherwise. One thing is that you are storing n squared divided by k edges, and k is very small. How do you store those edges? I mean, if you write their name, you have to pay log n bits for each of them. That's become more than the space you have. Okay. But if you think about it, n squared divided by n squared over k, like edges, information theoretically, you need log of these many bits to store it. So there are these things called succinct dynamic dictionaries that actually store the graph for like these edges in this information theoretically optimal space. This is now good for us. But then it means that from now on, you are not actually storing the edges. You are storing a representation of the edges in some compressed space. So everything you are doing has to work in this compressed space, but that can be done. Okay, good. And that's how do you get the result. Let me conclude quickly. So I show you the first non-trivial streaming algorithm for matching. 1 minus a small of 1 approximation, n squared divided by 2 to the theta log star n. And if you want polynomial time algorithm, then this factor becomes polylog star. Good. This is the first separation in the space complexity between better than half approximation versus exact answer. And An important property of this result is that if you have better RS graph upper bounds, that automatically give you better streaming algorithms. And if you improve the space of our algorithm, you get better RS graph upper bound. I don't want to oversell. There is a gap between these two. Okay, these two parameters do not exactly match. And the limit here will be n squared divided by 2 to the theta square root log. And that's all I wanted to say. Thank you.
Thank you, Sepehr. Just to maybe, okay, I run up.
Hi, Sepehr. I have several questions, maybe small ones. So first, sorry. Thank you. So better RS graph, upper bounds improve the space, and improving the space lower bound. Is it for 1 minus still the little one approximation, or 1 minus epsilon approximation? Improving lower bound of which improves the RS bound?
Good. Any better than 2/3 approximation?
2/3, okay.
Better RS graph.
Okay, thank you.
Just right around 2/3, the right upper bound, I think, is n squared divided by log n. Okay, because I told you RS graph, when the densities are like size of matchings are very close to half, there are slightly better upper bound. So I don't know, 3/4 for instance, no, sorry, less than that. Will be much, no, 3/4. So that is completely fine.
Okay. Okay, thanks. And another question. So in the algorithms for computing matching cover using the regularity Lemma's algorithm, you said you first store all edges instance to the noise part and some other edges. But if the graph comes in as a stream, you don't know the partition up front.
No, that's true. So that wasn't a streaming algorithm. There is a compiler basically that takes this non-streaming algorithm and turn it into streaming. That's come on top of this thing that I completely skipped basically.
Okay, thanks.
Yeah.
Can I ask a question?
Sure.
Oh, there's one. Oh, Asaf Shapira is on the Zoom asking you a question.
Yes, definitely.
Yes, Asaf.
Hey, so I just want to make sure that, so you said that there is this matching cover thing, this is n square over log star, but then you have the streaming algorithm, which is n square over 2 to the log star. So this is, so this doesn't use the matching cover, which is only n square over log star, or it's completely parallel, or it uses it?
Good question. So we have two matching cover algorithms, let's say. We have one constructive algorithm that gets a matching cover and creates n squared divided by log star n. That's constructive using regularity lemma. We also have another result that says non-constructively, let's say, you can bound density of matching covers by RS graph. So n squared divided by 2 to the log star n. The second result is, it's non-constructive. You can upper bound it, you can find that thing in exponential time, but it's not an efficient, we don't know an efficient way of solving that problem.
So if you could do the matching cover thing instead of n square over log star, let's say n square over 2 to the log star, then you would, or even better than this, then you will get immediately a better streaming algorithm, right?
Exactly, that's true. Yes, exactly.
Okay, got it. Thank you.
Sure.
Okay, this is, thank you for the talk. Let's, and we'll take the rest of the questions during the break. I want to give you a little bit of break. So, so let's thank Sepehr again.